I'm very pleased to participate of this important symposium. The title of my talk is a stepwise approach for high-dimensional Gaussian graphical models. This is a joint work with Lafitte, Nogales, and Samar, and the paper is going to appear in the Journal of Data Science, Statistics, and Visualization. A brief introduction. GGM, Gaussian graphical models, represent the linear dependency between variables. These linear dependency are measured by estimating partial correlations. There's a close relation between the non-zero partial correlation coefficient and the non-zero entries in the inverse of the covariance matrix. And covariance selection procedure estimate the GGM conditional dependent structure given a sample. Two problems: when P, the dimension, is larger than the number n of observations, the sample covariance matrix S is not invertible, and the maximum likelihood estimate of sigma does not exist. And when P divided by n is less or equal than 1, but close to 1, S is invertible, but ill-conditioned. To deal with this problem, to solve this problem, several covariance selection procedures has been proposed under the assumption that the omega, the precision matrix, is sparse. Basically, there exist three families or classes of methods: non-wide regression method, maximum likelihood methods like Lasso and Klein, and limited order partial correlation method. EPC, or equivalent partial correlation, belongs to this third group. We propose a new method, the StepGraph algorithm, or StepGraph, that estimates the graph using a forward-backward procedure. More formally, consider a multivariate normal vector of dimension P with posited the definite covariance matrix. A Gaussian graphical model consists in a pair BE. B is the set of nodes, and E, the set of edges, is defined by the following condition. A pair IG does not belong to E if and only if Xi and Xi conditionally to the remaining variables are independent. And then GGM can be effectively described by giving the system of neighborhoods AI I from 1 to P. Here you have three figures of the graphs of an autoregressive order 1 from left to right. In the middle, the nearest neighbor of order 2, and diagonal blocks models for P equal to 100 nodes. Okay, to represent these conditional dependent structures as a statistical model, it is convenient to find a parametrization for the set of edges. Consider the precision matrix, and let's beta IL, the regression coefficient of XL, in the regression of XI. Then the partial and the conditional correlation, that are the same objects when the distribution of the vector is normal, between Xi and XL can be expressed as a relation, it can be expressed as a function of the coefficient beta Li and beta IL. And this gives a parametrization for the set of edges. And moreover, there exists the following relation between the covariance of the regression errors and the variance of the errors and the elements of the precision matrix. Conditionally odds in neighbors, Xi is independent of all other variables. Therefore, given a system of neighborhood, and if a node L does not belong to the neighbor AI, the partial correlation between Xi and XL can be obtained by the following procedure. Regress Xi on the variables indexed with the nodes on its neighborhood AI and compute the regression residual epsilon I. Do the same with XL and compute epsilon L. And then calculate the Pearson correlation between epsilon I and epsilon L and compare with a threshold. This reasoning motivates the StepGraph algorithms. At each step K of StepGraph, we have a working system of neighborhoods. Then, if a node L does not belong to the neighborhood of a node J, one would expect, under this working assumption, that the empirical partial correlation coefficient is close to 0. And if the maximum absolute partial correlation computed this way is large, then we could conclude that the working system of neighborhood needs to be updated. We then add the most likely new edge, the one with the largest partial correlation, and this constitutes the forward step. And in the backward step, if the minimum absolute partial correlation coefficient between presently connected node J and L is too small, then this edge is removed. Here we have a more formal expression of the StepGraph algorithm. In every step, we do forward and backward, and we need a couple of thresholds to compare the covariance of the regression errors in order to decide to exclude or to include a new edge. Know that these thresholds that we call alpha forward and alpha backward, alpha F and alpha B, are selected by cross-validation. And the output of the algorithm consists of a collection of estimated neighborhood, the set of estimated edge, and an estimate of omega hat. We compare 3 models. Model 1, we described yet the autoregressive for the 1, nearest neighbor model for the 2, and block diagonal matrix models. 3 dimension values P, and for each P, we generate 50 random samples of size n equal 100. And for every model, we compare the 3 classical method, CLIMB, GLASO, and EPC, with a StepGraph and a slight modification of StepGraph 2. The performance evaluation is described by sensitivity, specificity, and the Matthews correlation coefficients. Heat maps are particularly useful, and the numerical performance of omega hat as an estimate of omega is measured by different distances and divergences. The conclusions, well, this paper introduced a stepwise procedure called StepGraph, use different parametrization of the GGM based on Pearson correlation between the best linear prediction predictor prediction errors. The algorithm begins with a family of empty neighborhood and using basic steps forward and backward, adds or deletes edges until appropriate threshold as reaches. These thresholds are automatically determined by cross-validation. StepGraph is compared with GLASO, CLIMB, and EPC under different models and using different performance measures. StepGraph is shown to have a good sample recovery performance and to produce more sparse models than GLASO and CLIMB. StepGraph is a parsimonious estimation procedure. StepGraph and StepGraph 2 compare well with standard procedures, including GLASO, CLIMB, and EPC. A particularly good simulation result are obtained under block models where the other approaches face some difficulties. We apply StepGraph for the analysis of breast cancer data and show that our method is a useful tool for application in medicine and other files. See the version of the paper in the web, in the archive web. Thank you very much for your attention. Here you have a very brief appendix and the bibliography. Thank you very much.